Welcome to this video tutorial about RHRV, R heart rate variability. RHRV is an open source package for the R environment which provides support for performing heart rate variability analysis from the RR time series. It has support for performing analysis on the temporal domain, on the frequency domain using both Fourier and the wavelet transforms, and nonlinear analysis. This video tutorial covers only the basic functionality of the package. For a complete reference for its functionality or more advanced functions, check the documentation in the RHRV website. The first thing you must do to use the RHRV package is installing it. You can do it through the install packages command of your R environment. It may download some other packages before RHRV on which our package depends. Then we load the package. You can see in the console how other three packages in which our package depends have also been loaded. And the first function from RHRV we're going to use is the function which creates a data structure where the RR series is going to be loaded and where all the results from the analysis are going to be loaded. That function is create heart rate variability data, and it returns a data structure which we have called hrv.data, where we're going to load the RR series and all the results from the analysis. We're going to change a property of this data structure, the verbose property, and we're going to set it to true. By default, most functions in RHRV do not produce any output in the console unless something goes wrong. If we set this property to true, all the functions are going to print messages in the console explaining what they have done. In my computer, in C/RHRV folder, I have a file called example.bits. That file contains an RR series stored in ASCII format. We're going to work with that file, so I'm going to move to that directory. And now we're going to load that file. RHRV has support for working with EDF, European data format, with Polar files, with Sunto files, with MIDBID files, and with several other formats. You can check that on the documentation. Here we're going to load the file which is in ASCII format. We just indicate the data structure where we're going to load the file, the name of the file, and the directory. The directory, given that we move to the directory where the file it is just a dot. We have load the data, given that this format of file, ASCII, does not have any information about when the recording was performed. The file data has been assigned the 1st of January of 1900. If we were working with EDF or MIDB or some other format which has information about when the recording was performed, that information will have been loaded in the RHRV data structure. We can see how we have loaded about 17,000 heartbeats. We can plot those heartbeats. Those heartbeats are stored as the time instance of each occurrence. Therefore, if we plot them, they are stored in $bits, $time within the data structure. Given that time, the heartbeats occur at consecutive time instance, the plot pretty much looks like a straight line. It's nothing really very useful. So the first thing we're going to do is to build the heart rate from the time of occurrence of each of the heartbeats, which is the information that we had stored in the file. We can do that with the build non-interpolated heart rate function. And now we can use the plot non-interpolated heart rate function to plot the heart rate. We can see here the heart rate. This recording was performed in an intensive care unit to a paraplegic patient which was tachycardic. We can see how the patient was at the beginning of the recording over 150 beats per second. About half an hour into the recording, the patient was administered some drug which decreased his heart rate. We can also see how there are a few values which are lower than average and some very high values, 300 beats per minute, 350 beats per minute. These values are impossible from a physiological point of view, and these values are really suspicious. These values are half of the average heart rate over here. These values have very likely been caused by failures in the heartbeat detector. The heartbeat detector has skipped one heartbeat. That means that we have an RR interval double the real size, and we have half of the heart rate. And these very high values are very likely artifacts in the electrocardiogram which have been identified as heartbeats by the heartbeat detector. Therefore, we have artifacts in this recording, and that's the most usual situation. Heartbeat detectors are quite good, but they make mistakes. So the first thing we must do is to remove these artifacts. We can remove them using the filter non-interpolated heart rate function. We see how this function has removed approximately 200 bits from the recording. It considered where they were artifacts. We can plot again the non-interpolated heart rate, and we can see that how we don't have a heart rate frequency of 350 anymore, and most of the low values have been removed. But I'm still pretty sure this value over here and this value over here at least are artifacts. The heartbeat detector has failed in detecting one heartbeat, and therefore I'm having half of the real heart rate. This may also be an artifact. I probably have a few artifacts here. So right now we can do two things. I can run again the filter non-interpolated heart rate function with different thresholds to filter, or I can perform manual addition. I'm going to do both things, therefore I'm going to make a copy of the data structure. The hrv.data.back is going to be our original data. And I'm going to filter again the hrv.data using the same function, but in this case I'm specifying a few parameters. The last two parameters are the easier to understand. This is the minimum allowable heart rate. Any value of heart rate below 25 is considered unacceptable, and therefore there was an artifact. And this is the maximum allowable heart rate. Any value over 180 will be considered an artifact. These first two parameters control the allowable rates of change for the heart rate. A heart cannot go from, for example, 50 beats per minute to 150 beats per minute in just 5 seconds. It needs more time. That rate of change is not allowed for the heart. The first parameter, it indicates a number of heartbeats which gonna be used to calculate an average heart rate. We're gonna use the last 50 heartbeats to calculate the average heart rate. And for the next heartbeat, we're gonna permit a variation of 10% respect the average value of the last 50 values. Basically, with these two parameters, I can define what rates of change are allowable and which ones are not. You see that the first time we used the filter non-interpolated heart rate function, we did not specify any parameter. This is how most functions work within RHRV. If you do not specify parameters, the library will use sensible defaults, which are probably right if you are working with human being recordings. If you, however, are working with animals, or if your patients are in some pathological condition or they are infants, you may need to change those default values. For example, we have used RHRV to analyze rat electrocardiograms. The rats, when they are at rest, their heart is usually beating between 250 and 350 beats times per minute. Therefore, its frequency is much higher. We could not use these thresholds. We needed to change these thresholds. So we have filtered again the heart rate using different values in the filter non-interpolated heart rate. I'm gonna plot again the non-interpolated heart rate, and I can see how indeed there's been some changes. I'm missing here a heartbeat, and there's probably a few other changes. If I change the output, the number of data points has decreased in approximately 200 heartbeats. Again, over 200 heartbeats have been removed by the second run of the filter non-interpolated heart rate variability. That may be too much. Maybe I have filtered things I didn't need to filter, so I'm not really sure if I'm doing the right thing. I'm gonna go back to the data that had been filtered with the default parameters for the filter non-interpolated heart rate function. I'm going back to that data. If I plot it again, you can see how again I have the two artifacts. And now I'm gonna perform manual edition of the artifacts. In order to do so, we can use the edit non-interpolated heart rate function. This function launches a new user interface which plots the heart rate and which allows the user to select artifacts by performing two mouse clicks. The two mouse clicks delimit a rectangle. All the heartbeats which are within the rectangle are considered to be outliers. If we click the Remove Outliers button, they will be removed. This over here may also be an outlier, so I could select it and I could remove it, but I'm not completely sure if that's an outlier. Maybe that's a real variation. So if we want to be 100% sure, we will have to check the electrocardiogram of the patient and the results of the heartbeat detection. So I'm going to leave that data point over there. I'm going to clear it. I'm not going to erase it. I click on End because I'm done. I have removed those 4 heartbeats which were really clearly outliers. If I plot again the non-interpolated heart rate, I can see how indeed they have disappeared. Right now I have an RR series which is outlier free. If I'm only gonna perform a time domain analysis, I'm set. But if I want to perform frequency domain analysis, I need to obtain a equally spaced time series from the original RR series. The original RR series is not equally spaced. Heartbeats do not occur at equal intervals. They occur when they occur. In order to interpolate the original RR series into an equally spaced time series, I can use the interpolate non-interpolated heart rate function. This function, one of the parameters is the frequency at which I want to perform the interpolation. If I don't specify it, it will use 4 Hz. 4 Hz is a sensible default if I'm working with human recordings. When we analyze rats, we use 16 Hz. You may use a value which fits your problem. Now I can use the plot heart rate function. This function plots the interpolated RR series and the interpolated heart rate of the patient. This series is equally spaced. I can't really tell the difference here in this plot because I have a lot of data points, but this series it is equally spaced. And now we're gonna start the analysis per se. The first analysis we're gonna carry out is gonna be a time domain analysis. In order to do so, we use the create time analysis function. We pass the RHRV data structure, which contains the RR series, and we specify a couple parameters. The first one is the size of a window in seconds, 300 seconds. This window is going to be used to calculate the time domain statistics within each 300-second window of the recording, and the final value for the statistics is going to be the average value from the results of each of the windows. And the second parameter, it is the width of the histogram that is used in the calculation of the heart rate variability triangular index and in the triangular interpolation of the RR intervals. For those two parameters, we need to plot the histogram, and this is the width of the bins of the histogram. These are the results of the analysis. These results have also been stored in the RHRV data structure. If you are familiar with heart rate variability analysis, you know the meaning of these parameters, you know how they are calculated. They are standard, they are pretty standard. If you don't know what they are, you may check the RHRV manual. We explain what they are, how they are calculated, and if they have a clear physiological meaning, what is the physiological meaning of that parameter. Here we don't really have too much time, so I'm not going to explain which is each of the parameters. Now we're going to perform a frequency analysis. First, we have to prepare the data structure to store the results, and we do so with the create frequency analysis function. And now we perform the frequency analysis with the calculate power band function. This function has many parameters, although I do not need to specify most of them. Here we have specified all the parameters possible. This function receives the data structure where the equally spaced sample time series must be stored. An index for the analysis. I can store multiple frequency analyses within the same RHRV data structure. Maybe I have performed those analyses with different parameters or with different techniques. So I must indicate the index of the slot where I want to store the result of this analysis. This is the size of the window where the frequency parameters are going to be calculated. It's a 300-second window. We're going to shift this 300-second window 30 seconds at a time, and we're going to calculate again the frequency parameters. We're going to do that throughout the recording. Therefore, each 30 seconds, we're going to have one estimation for the parameters, the frequency parameters, and we're going to build a time series which is has a sample each 30 seconds representing the values of the frequency parameters. We're going to use the Fourier transform. The size esp parameter is the number of points for calculating the short time Fourier transform. This parameter indicates that we use in Fourier, is the method by default. And now we indicate the limits for the ultra low frequency band, the very low frequency band, the low frequency band, and the high frequency band. All the values for the parameters shown in this sample run of the command are the default values. Again, you may change them if you want to, for example, analyze some animal recordings, or if you are working with recordings of people who are performing physical exercise, you probably want to use different limits for the frequency bands. All these results, of course, have been stored in the data structure. I could access to them programmatically within the R environment. We are just going to plot them using the plot power band function. Okay. Here we have the results for the ratio between low frequency and high frequency, ultra low frequency, very low frequency, and high frequency. This time series has been built, as I explained, by starting with a 5 minutes window, 300-second window. We calculate the value of all these parameters. We shift 30 seconds that window. We shift 10 seconds, 30 seconds the window. We said that the shift was 30 seconds. So we shift 30 seconds the window. We calculate again the parameters. We shift 30 seconds the window, and so on. Therefore, we have a time series of how those parameters have varied. We can see how in this point, which is approximately half an hour into the recording, there is a very clear change in the ultra low frequency parameter, and pretty much in all the parameters. Here's where it is really more clear. This is the moment where the patient was administered a drug to try to correct the high tachycardia he was suffering. We're going to create a second frequency analysis calling again the create frequency analysis function, we see how it's telling that now we have two frequency analyses within the data structure, and we're going to perform a second frequency analysis, but this time we're going to use wavelets. Observe how we have indicate that we want to store the result of this analysis in the second slot. The mother wavelet we're going to use is less asymmetric 8, and the band tolerance when we estimate the spectral power in each of the spectral bands is going to be 0.01 Hertz. This parameter means that this is a value in Hertz. If relative were true, this parameter would be a percentage of tolerance allowed for each of the bands. And again, we have the limits for the 4 bands. I can plot the results of this analysis the same way I plot the results for the first one. Again, I see very clear changes about half an hour in the recording. In our experience, we have used the wavelet transform in different studies with people and with animals, and in our experience the estimation of spectral power in each of the frequency bands with the wavelet transform is more accurate. It allows us to capture more subtle phenomena than the use of Fourier. After all, the RR time series, it is a non-stationary signal, and despite we are using short time, Fourier transform is not an optimal solution. This is everything we have prepared for this tutorial. If you want more information about RHRV, you may go to the RHRV website. Here you may find some news about late changes in the library conference where we are speaking. You have documentation where you can download the sample file we have used in this tutorial, and then you have the tutorial of RHRV. Is a quite complete long document. It has a lot of information and covers more advanced functionality than the one we have covered in this tutorial, so I recommend you check it if you are interested in knowing more about the tool. You also have forums where you can ask questions, submit patches, bugs, etc., etc. We have a list of publications where we explain how we have implemented the functionality of the library. And this is everything. If you use RHRV and you find bugs and you find something which is not working properly for you, please let us know. We want to improve the library, and if you are interested in contributing to the project, it's an open source project, go ahead, download the source code. We can help you with getting started. If you want to implement more functionality or provide support for some new data format or something, go ahead, your contributions will be welcome. Thank you very much for your attention.